Hello, I would like to present our work called Consistency Posterior Sampling for Diverse Image Synthesis for presentation at CVPR 2025. In this work, we're concerned with Bayesian inverse problems, which aim to invert noisy measurements to obtain the underlying cause X. And one way to provide solutions for noisy inverse problems is via posterior sampling, which aims to sample from the posterior distribution of X given Y. Current existing methods for conducting posterior sampling include diffusion posterior sampling, which leverages pre-trained diffusion models and conditions them on a function of the measurement y. In this case, the driving force of the diffusion process is the score function of the posterior x, and has two terms. The first being the prior score model, which is obtained via pre-trained diffusion models, and the second term is the likelihood function along the diffusion trajectory, which is in general intractable and must be approximated. A few downsides of these methods include that they target only point estimate or maximum a posteriori solutions rather than actually sampling from posterior, and it's also very inefficient to sample from these methods since they require simulating the full range of dynamics to obtain a single sample. In this work, we provide a solution which allows us to efficiently accumulate posterior samples. We do this by first of all viewing generative models as push-forward mappings from noise space or noise distributions such as the Gaussian onto the data distribution P0. And in general, we can refer to these two spaces as the noise space, or the support of the Gaussian, and the data space, or the support of the data distribution, which again are related via this generative model mapping phi. And the goal again is to sample from the true posterior of the data given the measurement y, which is the product between the likelihood and the prior of the data. And given our generative model mapping phi, we can obtain a model posterior which replaces the true data prior with our model of the prior. And finally, there exists a posterior in the noise space as well due to this one-to-one correspondence for our generative model mapping phi. And so our goal in this work is to sample from this noise space posterior and then map these samples back into the data space via our generative model mapping phi. And this can be accomplished using Langevin dynamics in the noise space, where Langevin dynamics simulates this limiting distribution P infinity given long enough simulation time. And so in order to sample from the noise space posterior, we can plug in the noise space posterior score, which has two terms. The first of which can be computed using automatic differentiation through the generative model mapping, and the second term is a simple Gaussian score. And finally, we can simulate from this SDE to obtain noise space samples, which can be accomplished using Euler-Maruyama discretization of the SDE. And again, the noise space posterior sampling corresponds one-to-one with a data distribution posterior sampling via the mapping of our generative model. For the practical considerations, we first consider an efficient generative model mapping phi, such as a consistency model that can alleviate the burden of differentiation through the generative model in each step. And this is due to the fact that consistency models allow few step sampling. We also accelerate convergence of the approach by warm starting this process with an optimization that minimizes the mean squared error. And finally, we're able to produce many posterior samples via Langevin dynamics, and we're able to control the stability and sampling speed via the tuning of the step size of the Euler-Maruyama discretization tau. To compare our method with state-of-the-art techniques, we consider application on linear and nonlinear inverse problems using pre-trained consistency models from the consistency model original paper. And we compare the fidelity and the diversity of the samples generated by these methods. In terms of fidelity, our method is able to achieve high fidelity, especially when compared with other methods using consistency model backbones, where our methods are shown as the second and first from the right columns. In terms of uncertainty quantification, since we're able to sample efficiently from the posterior and generate many samples, we can conduct uncertainty quantification by generating a diverse set of samples which highlight the highly uncertain or highly certain regions shown in the samples on the screen here by red and green boxes. And this can be done at scale with many different samples and many different examples in this LSUN dataset that we've evaluated on. And so overall, we have developed an efficient method for accumulating posterior samples by leveraging generative model mappings phi. Namely, we leverage few-step generative models such as consistency models that enable this generation to scale up to very many posterior samples. And due to this fact, we're able to achieve uncertainty quantification via the generation of a diverse set of samples, and we're able to highlight uncertain features in the posterior.